So let's return and talk about non-uniform circular motion. So the difference is the speed. In uniform circular motion, the speed is a constant. The magnitude of the velocity is a constant. In non-uniform circular motion, the speed is no longer a constant, which means we must have some component of the acceleration in the direction of the velocity so that it changes. The velocity has to remain tangential to the trajectory, but its magnitude is going to change. So the diagram changes a bit. We have our radius vector, always having constant magnitude. We have our velocity vector, always remaining tangent, but now our acceleration vector has to have a radial component and a component which is tangential. All right? And I'm going to call those two components of the acceleration the parallel and perpendicular components. Parallel and perpendicular to the velocity. So there'll be one component of the acceleration which changes the magnitude of the velocity, and there'll be another component of the acceleration which changes the direction of the velocity. The velocity still has to move along this circular arc, which means that it still has to have a perpendicular component to it to make it move in a circle. But now it has this parallel component that's going to change its magnitude and thus change the speed. In fact, the perpendicular component, which I'll show you later, still must have the exact magnitude that it had before. It must be r omega squared in the radially inward direction, or v squared over r in a radial inward direction. So that amount of acceleration to keep the particle moving in a circle hasn't changed. What has changed is that omega and v are no longer constants. So the classic example of this is the swinging of a pail. So if you take a bucket and you swing it around in a vertical direction, it's going to have two forces on it. It's going to have a force radially inward due to your arm, or due, I'm going to call it, to a rope, and it's also going to have a downward force due to gravity. And so the bucket will swing more rapidly down at the bottom and less rapidly up at the top. And so this is an example of non-uniform circular motion. The bucket is still moving with a constant radius, that's why it's circular motion, but it's non-uniform because its velocity is no longer constant. So if we look at the forces on the bucket, the trajectory would be going like this. We have the tension due to the rope. We have some component of the gravity which is radial, and this will depend on the angle. And we have some component of gravity which is tangential. So gravity is operating downward, and if you added these two components up, you would get a vertically downward force given by gravity. If we label this angle to be theta, we can find what the tangential and radial components of the gravitational force are. The tangential component is minus mg cosine of theta, this component. And so when theta is 0, this is just equal to minus mg. A particle out here has the full gravitational force being tangential. The radial component is mg sine of theta, so that when theta is equal to 90 degrees, the radial component is mg. And I've labeled this so that the radial component is always positive as it's directed towards the center of the circle. So this will be a positive radial vector, and this will also be a positive radial vector. A negative radial vector will be one which is pointing away from the origin. So then what we know is that the total radial force, that being the tension in the rope, plus the component of gravity which lies along the radius, must be equal to minus v squared over r in the inward radial direction, or equivalently, it's equal to m r omega squared. So this is really important, I can't stress this enough, that the sum of these two vectors must always instantaneously be equal to mv squared over r. Okay, so I wrote a code to simulate the motion of a particle moving in non-uniform circular motion. And in the first case, what we did is we started with a rather low initial angular velocity of 1 radian per second. We let the particle start at rest at the bottom, And the motion that we see is at the white trajectory here. And what I've shown is the tension in the rope in this blue arrow. So the tension is pulling up, and it still has gravity operating downward. I haven't shown that vector. And the particle is just moving back and forth, back and forth, back and forth. So what are the quantities that one would like to look at to examine this motion? Well, the angle as a function of time, that might be one. The angular velocity as a function of time would be another. And then how about the force, the tension in the rope, as a function of the angle? So I've graphed those three quantities here. So here's the angular velocity as a function of time. So we have theta versus time. And what we see is we started it off at the bottom where the angle was equal to 0. And it goes up to about 0.3 radians, or somewhere about 18 degrees. And then it just has what looks to be a very sinusoidal swing back and forth, like a pendulum. All right? If we look at the angular velocity, we see that it also looks sinusoidal. All right? And it's out of phase with respect to theta. So that we started at the bottom where the theta was equal to 0, but the angular velocity was a maximum. It was a maximum clockwise velocity. That's the way I chose to start it. When the angle got to its maximum counterclockwise direction, this is actually a counterclockwise velocity, when it got to its maximum counterclockwise angle, our angular velocity had gone to 0. When it passed through 0 degrees again down at the bottom, we had our maximum negative angular velocity. And so this is an example of simple harmonic motion, again, or very close to simple harmonic motion given by a sinusoidal wave. If we looked at the tension in the rope, we see there is some variation in the tension. What would the tension be if we just hung the mass at the bottom and just let it be rest? Well, mg for a bucket of mass 1 would just 1 kilogram would just be 9.8. So this would be what the tension in the rope would be if it weren't swinging at all. The tension is actually a little bit greater than that because we have to have the tension being equal to a radial component of the tension be equal to mv squared over r. So this tension has to overcome the force due to gravity and supply a radially inward component, and that is this component right here, necessary to have it move back and forth. So this was an example of a low amplitude oscillation of the bucket on the end. Let's have the bucket have a larger amplitude of motion. So that's depicted here in this trajectory. So here we have the arc swinging quite a bit farther, 78 degrees, 1.3 radians. So the bucket is now swinging back and forth, back and forth. A couple things you can note here is that it still looks rather sinusoidal, but in fact it's changed. The period is no longer the period that one would expect for simple harmonic motion. It's increased to 2.25 seconds, whereas before it was 2 seconds before. Now it's 2.25 seconds, so it's increased. And the angular velocity, you can notice, actually doesn't look sinusoidal anymore. This is actually starting to look more like a triangle wave. You may not have looked at enough sine functions to know this, but this is too sharply peaked here. So our angular velocity looks more like a triangle wave, and our period has changed. We're no longer in the case where this can be described very well by simple harmonic motion. However, the most obvious change is actually the tension. If we look at the tension as the bucket swings down through the bottom of its trajectory, it's up close to 28 newtons or so. So that's almost triple the weight of the bucket at the bottom. Whereas out at the edges, when it's fully out, the tension is close to 0. We're down to something like 2 newtons out at the edge. So the tension in the rope, as this is swinging back and forth, the tension is quite high when it's down at the bottom moving rapidly. But up here at the top, the tension is very little. It's not providing much of a radial inward force. So if we increase the angular velocity even further, then we get an angular progression which is clearly not sinusoidal. This is much too round for sinusoidal motion here. The period has also continued to increase, so we're now out over 3 seconds for a period. I've increased the angular initial velocity to 6 meters per second. This can be, and the changes from simple harmonic motion are really obvious here in the angular velocity. Not only does this look like a triangle wave, it actually has inflection points here. All right, so this is clearly a very different angular velocity than what we've had before. But the largest difference is actually in the tension of the rope. So the tension down at the bottom at 0 angles is quite large, so it's more than 4 times the weight of the bucket. But as we go out towards the edge, the tension actually goes through 0 and the tension turns negative. So here is the trajectory. The bucket is swinging more than 90 degrees positive and more than 90 degrees negative. So the bucket is actually going up here. And the tension points in the opposite direction. The tension in the rope is pointing outward. Now, can we have a negative tension in a rope? The answer is no. A rope can't push the bucket outward. So this motion, this type of motion, is not possible for the bucket. We've been able to create circular motion which doesn't fit the physical situation. Now, there are physical situations where this is realistic. If I had replaced the rope by a stick, then the stick could actually pull on the bucket inward as the rope can, but it could also push out on the bucket, pushing it outward. So depending on what kind of rod or what kind of tether we had between the bucket and our arm, our hand providing this motion, we could have this type of motion, but we couldn't have it with a rope. So the tension points radially outward in these regions where it's negative, and then it is radially inward for the rest of the trajectory and becomes 4 times the weight down at the bottom. So if we now replace our picture having a rope there and say have our arm or a stick, we could actually have this motion, but sometimes we would not only be pulling in on the bucket, but sometimes we'd have to be pushing out. So we can take this even further and now provide the motion that's necessary for the bucket to get up to the top. All right? So we can take the bucket and have it start at the bottom, give it just enough velocity to swing all the way up to the top. There's a very special velocity, and we'll later learn how to calculate what that velocity is, but right now it's very close to 6.24 meters per second. So I'm going to show you 2 trajectories. One is going to start off with a slower initial trajectory, 6.24 meters per second, and then I'm going to increase that by 1%, 6.27 meters per second squared. So with a 1% difference in the change in initial conditions, we're going to get quite different trajectories. So starting with the low initial velocity, this is what the progression of the angle as a function of time looks like. It has a very flat top up here around theta is equal to 3.14 or pi. So what is that? That means that the bucket has swung up to the top, slowed down, is approaching the top, and progressing very slowly. That's what this flat top is right here. Then it will turn around, swing back down through 0 degrees, and go up to the top on the opposite way, swinging around this way, approach the top very slowly, not make it over, and then go down. So that's the motion like this. And you can see that we have theta being bounded by plus pi and minus pi. Looking at the angular velocity, you can see that as in fact it approaches the top, which is right here, we almost go to a 0 angular velocity. We almost stop. All right? But actually it flipped sign. It was moving upward, going counterclockwise here. It reaches 0, and now it moves clockwise down here, falling in the opposite direction. So this is the angular velocity as a function of time. Our tension really hasn't changed very much. It still goes negative up at the top and looks very similar to the case that we had before. Okay? Now, let's increase the initial velocity by 1% and see what change we get. So this is now the progression of the angle as a function of time. It looks very different than we have before. There's no way you could possibly confuse this with some sort of sine wave or oscillatory motion. Theta as a function of time is an ever-increasing function. And what this means is that the bucket is going around and around and around, and every time it does that, we add 2 pi to our angle. So we started down at the bottom, we've reached the top, we go over the top, we get down to the bottom again at 2 pi after we've gone 2 pi around, and we keep on going up to the top again. So these plateaus are all separated by 2 pi as it's gone around and reached the top. The angular velocity now has only one sign because we're continuing to go counterclockwise the entire way. So this was our initial angular velocity, 6.27 radians per second. And it gets close to 0 as it goes to the top, but it never goes through 0. It stays positive. So we keep winding around counterclockwise, slowing down, speeding up, slowing down, speeding up. So this is very, very different from what we had before. Here is the tension as a function of time, and this may look quite different from the tension we had before, but in fact it's really the same. What's changed is the angle is no longer bound by plus minus pi, but is winding around continuously. So what we had before was simply an arc that, say, went from here to here. And those were the only things that we could see. Now we just have this unfolded as the angle continually goes around and around. But the tension is basically the same as it was. Now, can we never have the bucket swinging around and around? Well, we can actually with a rope, but what we have to have is it go fast enough so the tension is always positive. And so we have to swing it with an even higher initial angular velocity. If we go up to an angular velocity of the square root of 5g over r, and you'll learn how to calculate this later in class, or an initial linear velocity of 7 meters per second, then theta increases with time. It looks more linear. We see less variation between slowing up and stopping down at the bottom. But the important thing is to look at the tension. All right? So again, our angular velocity is always positive. We're always moving counterclockwise around. But the tension now is large and positive at the bottom, but it remains positive at the top. Or in fact, for this particular condition, it just gets to 0 at the top. And so we always have a positive tension on the bucket, and a rope can supply that. So we can swing a bucket around and around, but we have to have a large enough velocity. All right? So this is a fairly complete discussion of circular motion, both uniform and uniform circular motion. The most important things for you to realize are that it is an accelerated motion. Even when the speed is constant, you must have an acceleration which is radially inward of a particular magnitude. Now, that magnitude, v squared over r, or r omega squared, is what's necessary for the radial component for either uniform or non-uniform motion. There's one last thing I'd like to talk to you about, and that is I've never used the word centripetal acceleration here. And I would just assume that you lose that from your vocabulary. Centripetal acceleration is a description of the resultant force on a particle moving in a circle. In other words, after you add up all the real forces, you're going to have a radially inward force equal to mv squared over r. That gets labeled the centripetal force. It can be due to gravity, it can be due to tension, it can be due to electrostatic, magnetic. It's due to some real forces, all being summed together to give at that instant in time an inward force of magnitude mv squared over r, or mr omega squared. There is no such force as the centripetal force that you can place on a particle. It's a resultant force. Students look to draw free body diagrams and place something on their particle called the centripetal force. That's wrong. Don't do it. It's best if you just lose the idea of centripetal force and just deal with real forces. Gravity, tension, whatever. Just deal with real forces. All right. The last thing I do in my notes is I prove that for non-uniform circular motion, the radially inward component of it has the magnitude that I've been telling you about. And so what we do in this proof is we say let theta of t be some arbitrary function. It's a non-uniform circular motion, so we don't know whether theta is going back and forth or around, speeding up, slowing down. It's some arbitrary motion. The trajectory then is going to be r times the cosine of theta of t x hat plus r sine of theta of t y hat, where theta of t is this arbitrary function. Omega is again the angular velocity, but it's now the derivative of theta as a function of time. So in the simple case where theta was equal to omega t, when we take the derivative of this, we just get omega of t is equal to the constant omega. But now we're looking at the more general case. So differentiating this expression for r with respect to time, we find that the velocity is equal to r d theta dt, which is going to be equal to omega, times minus sine x hat plus cosine of theta y hat. And so this is r omega of time, the instantaneous angular velocity, times v hat. We're taking another time derivative. We now get something that's more complicated because we had two parts here which had a time dependence. We had this part which has a time dependence, but we also have the angular components here that have a time dependence. So the first thing that you get is r omega squared times minus sine theta of t x hat plus cosine theta of t y hat. So that's one component. And this component that you'll see is parallel to the velocity. So these have the same, these are parallel to one another. Now we have a part which is perpendicular to the velocity. Taking the derivative of this part, we have r omega squared d theta by dt quantity squared, and then we take the derivative of the angular parts. We get something which is now parallel or anti-parallel to the radius vector, like we had before. So recognizing that this is parallel to the velocity and that this part is parallel to the radius vector, we can write this then as r d omega by dt times v hat minus r omega squared r. This is what we've been dealing with before. This is the radially inward component of the acceleration, which has magnitude r omega squared. Just as I've claimed earlier, we now have a new part which is parallel to the velocity. This is the acceleration parallel, which changes the speed. So it's conventional to find the change in omega with respect to time as the angular acceleration. This is a change in the rate of change of the angle. And so if we look at that, we can write the acceleration as r times the angular acceleration v hat minus r omega quantity squared times r hat. And so this can be recognized as our parallel component of our acceleration and our perpendicular component of our acceleration, just as we had drawn earlier in the diagrams. So this then proves that no matter you have uniform circular motion or non-uniform circular motion, you have to have this inwardly directed acceleration of the magnitude r omega squared, even if omega is changing as a function of time. And so I'm also going to now show you these simulations which allow the motion to be shown dynamically, and you can look at these graphs, and it's important for you to understand what's going on in these graphs. Don't just look at them and say, oh, that's an interesting picture. Actually understand what the maximums, what the minimum, what the time is. That way you'll learn about the motion. I'd like to show you the simulation for non-uniform circular motion. This is a situation that was appropriate to having a bucket being swung around in vertical plane with gravity present. So the variable parameters are what angle you start it, what initial velocity the particle is given, its mass and such. So I have used a rope length of 1 meter, a mass of 1 kilogram. I'm always going to start it in the downward position and give it varying initial angular velocity. So let's start out with initial angular velocity of 1 radian per second, and since we have a radius of 1, it'll be 1 meter per second as well in terms of the linear velocity. So over in this window, you will see the trajectory traced out in white. It's just a pendulum going back and forth. The blue vector is the tension in the rope. And you can see it gets longer as it crosses down through the middle. Over on the right-hand side, we have the graphs that I showed you in the notes. So we see the angle theta, which has about an 18-degree excursion, oscillating to the positive and to the negative, the angular velocity, and then here is the tension. All right, so let's go and increase the initial angular velocity to 4 radians per second. So now we have quite a lot larger amplitude, and you can see that the tension in the string almost vanishes at the turning point where it turns around and gets quite large down at the bottom. And so that's reflected in the tension down here, showing quite a large value, roughly 3 times the weight of the mass, and then going close to 0 as it heads out to its largest excursion. And this is no longer simple harmonic motion. This is no longer a sine wave. And that's most easily seen by looking at the derivative of it, or the angular velocity, which I said looks a bit like a triangle wave. All right, so let's carry on further and go to an initial angular velocity of 6 radians per second. And then here you can see the first time that the tension goes negative. And so some of the times the rope is placing a positive tension, which is what ropes can do, but other times it's putting a force that's pushing it outward, which ropes can't do. But you could use your arm or you could use a stick. And now looking at our theta versus time curve, you can clearly see this is no longer simple harmonic motion. The velocity is very strange. It has these inflection points in it. And as I stated, the tension actually goes negative for a certain range of the motion. Increasing the angular velocity even higher, we go to 6.245. And so this is a velocity that just about gets it up to the top. And you can see it slowing down as it goes there. And this is reflected in the strange looking curves for the angle versus time with a very flat top, and the angular velocity versus time, which then has this inflection here as it almost goes to a horizontal line. Again, the tension goes negative as it did in the previous graph. It just goes for a little far larger angular excursion. But let's increase this initial angular velocity by 1%, so 6.276. Run it again, and now what you see is the ball just makes it over the top and goes around. It still has the negative tension as it's going over the top, so this could only be done with a stick, not with a rope, but it makes it over. And so now your angle as a function of time progresses uniformly up, increasing as it goes around and around. Theta is defined from minus infinity to infinity, so every 2 pi it just adds on, it doesn't repeat itself. The angular velocity was always counterclockwise, in other words, always positive. It never crossed through 0. It was low while it was at the top, and it rapidly changed as it went down through the bottom. And the tension looks the same, except for the angular excursion is now drawn out in a repeating theta. So on the last graph, let me increase the initial angular velocity to 7. And here what you're going to see is the motion will look qualitatively the same, except that you'll notice that the tension vector goes to 0 at the top. It's no longer positive. All right, and so we can see that we've hit this critical value where the tension always remained positive, so a rope could actually swing a bucket at this velocity. So if you had water in your bucket, you'd actually not get any of it spilled out, whereas in the previous couple cases, water would be spilling out. If I go to an even higher angular velocity, let's go to an angular velocity of 9. And now you'll see that there's always a positive tension. And so this is rotating more rapidly. The rope is always applying a tension. The angle is just growing almost linearly with time. Gravity is almost not playing a role. You can see there's not a large change in the angular velocity as this goes around, and your tension is always positive. So this would be a bucket that's swinging quite rapidly around.